ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
Okay, in the last class we talked about what is called as stress tensor, and we had completed our discussion on tensor, saw that it is symmetric and so on. One of the questions that can come to your mind is that in your earlier classes you would have probably studied about shear stress and normal stress. In fact, what probably would have studied is in any plane you can find out what is called as the normal stress and shear stress. How is that related to what we have studied? Okay, there can be a question in your mind. In other words, you would have studied about principal stress and so on. We will come to the principal stress in a minute, but before that let us see what this normal stress and shear stresses are. Please note that we started our discussion by defining what is called as a stress vector. The normal stress and shear stress are nothing but are obtained by how? Resolving my stress vector, whatever I obtain, from the formula which I derived for it from stress tensor, either perpendicular, in which case I get normal stress, or along the plane, in which case I get the shear stress. So we are right in the same path as what you would have studied. It is not that whatever you have studied is not right or something like that. We are at the same path, but we are putting it in a more rigorous fashion, that is all. So that is called as normal stress and shear stress. And the other question which we were just started is, if I have a bar and if I do a tensile test, okay, I get what is called as the yield strength of the material, sigma y. Now I have just now shown that stress tensor has 6 quantities, 9, but because of my relationship that sigma ij is equal to sigma ji, I have 6 quantities. The question that may come to your mind is, I have only one value as a material property, I have 6 values as stresses. Now how am I going to tackle the situation? Or in other words, the question is, can I somehow combine these 6 chaps into one fellow, some sort of an equivalent criteria for a uniaxial. Please note this is a uniaxial situation. Can I get an equivalent uniaxial stress and compare that with the yield strength? Yes, that is possible, and the corresponding theory relies on or is called as Mises stress. Let us go back to our slide, what we were looking at in our previous classes. Look at that slide now. You see that what we are seeing is Mises stress. Okay. We did a contact analysis of a wheel and axle together, and what we were seeing is what is called as a Mises stress. Let us look at the next slide and see what we are looking at. Again, see that clearly that it is Mises stress distribution. In other words, it is possible, the theory of which I will explain, it is possible to get one equivalent stress, okay, called the Mises stress, one equivalent stress called the Mises stress, and then compare it with the yield strength. For example, whatever stress value I have in this particular transparency or slide rather, I will straight away go and compare it with the yield strength of the material. It is about 37 kgf per mm squared or 370, around 370 Newton per mm squared. I will straight away compare whatever value I am getting there to the yield strength of the material I have obtained from my uniaxial test. Okay. So, let us look at the next transparency or next slide. Here again you see that we are looking at Mises or von Mises stress, okay, again from Mises theory. So, all these things from all these examples we notice that we look at what is called as the Mises theory, or we look at what is called as the Mises stress. Now, in your earlier classes you would have called this theory as failure theories. And probably you would have called this as distortion energy theory. You would have studied a number of failure theories. You would have studied what is called as a maximum shear stress theory called Tresca's theory. This is due to a person called Tresca, and you would have studied distortion energy theory, and which we will now replace it with or call this as Mises theory. Now, this term failure theories is a misnomer, and unfortunately students do not pick that up very clearly. Failure does not mean fracture of materials. A lot of people make this mistake. Failure theories do not mean that when Tresca's criteria or Mises criteria is satisfied, the material is going to break into two. No. For design purposes, it has long been assumed for 100 years now that if the material starts yielding, it will not serve the intended purpose. This is what was first thought about, and hence they say that failure means, this failure means not fracture, but failure to do the intended purpose. That is what is meant by failure theories. It is not fracture, it is not failed means it is not fractured, but intended, it failed to do the intended purpose for which you have designed the component, and hence people started calling this as failure theories. But the current terminology today is called is not failure theory, but they are called as yield theories. Or in other words, these theories, since they signify the yielding of the material, in other words, yield theories are nothing but yield criteria to signify that the material is going to yield. In much more simpler terms, failure theories signify a criteria for the material to yield. So, that is what we usually call this as, I mean that is what we mean when we call things as failure theories. Now, in order to go into the details of this, we need two things. One is, in order to define or in order to explain Tresca, one is that we have to define principal stress, and the other we will do is to decompose the stress tensor in order to arrive at the theory due to Mises. In most of the finite element packages, people look at what are called as Mises stresses, and hence it is very important we understand what is the basis of defining Mises stresses and what exactly it means, or else we will not be able to interpret the results. Now, before we go to Mises, let us look at what are the principal stresses. All of you know, I am sure, what a principal stress is, but we are going to do the same thing in a slightly different setting. What is the setting? Now, we have been looking at a complicated component with certain boundary conditions and certain loading conditions and so on, and we were always looking at a point inside this. Now, the question is that if I consider all the planes passing through this point, can I get a plane or more than a plane where or on which the stresses or stress vector is wholly normal, completely normal. Okay? In other words, can I get a plane or more than one plane where shear stresses are absent? Or to put it more clearly, can I get planes where my stress vector, please note the stress vector, okay, is in the same direction as that of n. So, that is the question. Yes, that is possible, and such planes are called as principal planes. How do I write this mathematically? I write it mathematically by saying that Ti is equal to sigma Ni. Ti is equal to sigma Ni. Okay? In other words, this sigma is the magnitude of the stress vector which is totally normal to a plane whose normals are defined by these n's here. So, in other words, please note when I resolve here T1, T2, T3, they are along 1, 2 and 3 direction. In other words, suppose I assume that this plane is the, if I assume that this plane is the principal plane, then if that is the normal, then what I mean to say is the stress vector will be along that. And what I mean by T's is, please do not get confused, is how I am going to resolve T in 3 directions. That is what is meant by T1, T2 and T3. Let us go one step forward and write that equation with the result which we know for T. What is that result? Sigma ji nj is equal to sigma ni. Okay. Now, compare this with, for example, an equation of the form Ax is equal to lambda x. Say A is a matrix, x is a vector, and Ax is equal to lambda x. What kind of problem is this? Correct. So, it is an eigenvalue problem. Compare this equation sigma ji nj is equal to sigma ni with this equation. Do you see that there is a similarity between the two? Yes. So, what does sigma actually signify? You can treat this as a actually a simple matrix in order to understand it, though the concept may be slightly deeper than that, but nevertheless right now it is easy to just treat this n as a vector, 2 vectors, and you can look at this as a matrix. So, sigma n is equal to some sigma into, please note there is a difference between these 2 sigmas, into n. Okay. So, what is this? This is nothing but an eigenvalue problem of this sigma, or in other words, principal stresses are nothing but the eigenvalues of this stress tensor sigma. Okay. They are nothing but the eigenvalues of the stress tensor sigma. Since sigma, we have shown a lot of properties for sigma, it is symmetric, we can have many more properties we will define later, and hence it is possible to say that this sigma has eigenvalues and hence say that they are principal stresses, or in other words principal stresses come about because there is a property called eigenvalue for this matrix sigma or a tensor sigma. Okay. Though we started from here and came here, you can always go from here back to here and say that yes, if I get eigenvalues, what does it mean? It means that they are nothing but the principal stresses. Is that clear? Okay. Now let us write down Ni in terms of delta ij sigma nj. Delta ij nj. Okay, Ni becomes delta ij nj. So that equation can now be written as sigma ji minus, I am bringing that to the left hand side, minus sigma delta ij nj is equal to 0. Is that clear? Is that clear? Okay. Now what else do you get from that equation? Or in other words, how many equations are there, by the way? 3 equations. Okay. You can, if you want, you can write it down as sigma 11 minus sigma n1. Let me write down the first equation, sigma 11 minus sigma into n1 plus, what is the second part? Sigma, now you know sigma 12 is equal to sigma 21 and so on, so it does not matter because that makes it easier. So you can say sigma 12 n2 plus sigma 13 n3 is equal to 0, and you can write down 2 more equations. So in order that we have, by the way, before we forget, what is this delta ij, by the way? What is this? Remember? Kronecker delta, and what is that? That is nothing but an identity matrix. Okay, please remember that. And now what does this tell us from our very fundamental linear algebra? I can have 2 types of solution. One is a trivial solution for n1, n2, n3. Okay, which means that they all of them are 0, and hence this equation is equal to 0. But if I want to have a non-trivial solution, what is the condition I should have? If I have to have a non-trivial solution, then exactly, so the determinant of the coefficients should be equal to 0. So in other words, I can say determinant of sigma minus sigma I should be equal to 0. Is that clear? So sigma minus, see, please note the difference between this sigma and this sigma, always it is like that, okay, but I am sure that the squiggle below will tell you which is a tensor and which is a scalar. Is that clear? Okay. So what do I get from this equation? From this equation I can get a cubic equation, I mean, or from determinant sigma minus sigma is equal to 0, I can get a cubic equation, and the cubic equation can be written as sigma cubed minus I1 sigma squared minus I2 sigma minus I3 equal to 0. Okay. Now what I have done is I have just left some of the steps, you can easily fill it up. That determinant is now expanded and written. Okay, I get a cubic equation which is given by this particular form, where I1 is equal to sigma I. What is sigma I? Trace of sigma, correct, trace of this matrix called sigma. I2 is equal to half of sigma ij minus I1 squared, and I3 is equal to determinant of this matrix sigma. Now, how I hope you all understand how I got it. I just got it by taking the determinant of that determinant of sigma minus sigma I. Okay? So, I have got this. Now, what are I1, I2, I3? I1, I2 and I3 are called as invariants. See, in solid mechanics we have very nice names. Okay, the names signify or have lot of meaning to it. So, when I say invariance, it has a lot of meaning to it. So, it means it does not change, invariant, it does not change. It does not change with respect to what? Why do you call it as invariant? Is it with respect to plane? Because look at this equation and tell me. Okay, let us just slightly go back, because a very important concept which people usually do not understand. See, look at this equation here. I have got this equation and I want to find out sigma, okay, and sigma, which is the principal stress. I would say, I would not call it a sigma, let me say that I want to find out the principal stress. And what is it that I have been given? I have been given the stress tensor sigma ij. Obviously, the stress tensor, okay, is a function of how I have chosen x1, x2 and x3 or coordinates. So, the final equation which I should get and I should solve should be such that the principal stresses should not be a function of coordinates, correct. So, it should be independent of the coordinates which I have selected, or else I can get whatever I want, because principal stresses, okay, have to be determined without the interference of these coordinates. So, what does it mean? It means that this equation which I am going to solve in order to get my sigmas should be invariant to the coordinate system. Hence, the invariance signify or says that they are independent of the coordinate system which you have used in order to get the cubic equation. Is that clear? Okay, hence they are called as invariants. Now, once I have this, it is not very difficult, it is very straightforward to find out I1, I2 and I3, and once I know what are I1, I2 and I3, I can very easily substitute them in this equation, solve this cubic equation. You know so many methods to solve them. What is the simplest method you can use? Trial and error will be too difficult. Newton-Raphson or Newton's method can be used in order to solve them. There are very well programmed, I am not going to the details of it. If you have difficulty, let us see it, but I think it is a straightforward method to solve the cubic equation. Once I solve the cubic equation, I can get, okay, n's. So, first of all, when I solve the cubic equation, what is that I am going to get? I am going to get 3 values of sigma. In other words, I am going to get sigma 1, sigma 2 and sigma 3. Okay. Corresponding, so what are these things? Sigma 1, sigma 2, sigma 3, they are the eigenvalues of sigma, of the matrix sigma. Okay. So, corresponding to this, there should be eigenvectors. Okay, there should be eigenvectors. In this case, what are these eigenvectors? They are the principal planes, they are the n's. Okay. So, for each of these eigenvalue, I will get one set of n's, which I can get by solving the equation which we have written there. Okay, just now we saw that equation along with the fact that Ni are n1 squared plus n2 squared plus n3 squared is equal to 1. Okay. By solving these two, we are going to have, or we will get an equation, or we will get a set of equations to get Ni's. So, n's are eigenvectors, and please go back to your theory on principal planes. What is an important theory which you would have studied? Principal planes, do they have a relationship? Principal planes perpendicular to each other, this is what you would have used. Principal planes are perpendicular to each other. A more sophisticated way, you say that they are orthogonal. Why? Because eigenvectors are orthogonal. So, you see that whatever you have studied, okay, before comes beautifully from our theory that we can define stress as a tensor and so on. Okay. Hence, these principal planes are orthogonal. Once I define principal planes, I can get the maximum shear stress. I am not going to the details, you know it already, that the maximum shear stress can be defined as, how do we define maximum shear stress? Say, let us say that the maximum shear stress is tau. Correct. So, that is equal to sigma 1 minus sigma 3 by 2 after arranging sigma in a descending order, sigma 1 being more sigma 2, more than sigma 2, and sigma 2 being more than sigma 3. So, the shear stress, maximum shear stress is given by sigma 1 minus sigma 3 by 2. And we also know that in the planes where maximum shear stress exists, there are normal stresses and so on. Okay. Again, this is a fundamental strength of materials. Okay. So, Tresca's theory simply states that when maximum shear stress reaches a value which is obtained by an experiment where the shear stress reaches a critical value, or in other words, when tau reaches a critical value, then we have yielding. Okay. So, in a uniaxial situation, what is that? Sigma y by 2. So, a critical stress in the uniaxial situation is sigma y by 2. So, when tau reaches sigma y by 2, we say that yielding has occurred according to Tresca's theory. But Tresca's theory is valid and it is quite good, but there are certain difficulties which we will not discuss it right now. Okay. But it can also be used, but more important theory that is used for metals is what is called as the Mises theory. So, in other words, whatever we saw just now, we saw that principal stresses can be arrived at very naturally from our definition of stress, and is quite useful as well if you are going to use Tresca's theory or certain brittle materials where you can use the maximum stress theory as well. In other words, you can say that the maximum stress is one which will signify my failure and so on. Okay. I am sure all of you have studied this in your design courses, so I am not going to repeat that. On the other hand, let us go to what is called as Mises theory. Mises said that the stress tensor can be decomposed, more importantly additively decomposed into two parts, which he called as dilatational and deviatoric. He said that the stress tensor can be additively decomposed into a dilatational part and a deviatoric part. A dilatational part is also called as the hydrostatic part and a deviatoric part. In other words, what he physically said is that the stress tensor can be split into two parts, one responsible for volume changes, okay, the other for distortion. So, deviatoric is also called as distortional. So, one part responsible for volume changes and the other part responsible for distortion and that part is called as deviatoric part. He defined the dilatational part, because note the word hydrostatic part or the dilatational part, by a tensor which he wrote like this, where what is P? P is equal to, correct, sigma II by 3. Okay. So, he said that the whole of this sigma tensor can be split into a dilatational part and a deviatoric part, which comes out, now I said it is additive decomposition. So, what should be the other fellow here? He should be sigma 11 minus P, sigma 12, sigma 13, sigma 21, sigma 22 minus P, sigma 23, sigma 31, sigma 32, sigma 33 minus P. Okay. So, I hope it is clear, maybe write it slightly further away. In other words, when I add these two, I will get my original sigma matrix. Is that clear? Okay. Why did he do this? He did this because he found out, he and many others found out, that of these two parts, it is the deviatoric part which is responsible for yielding, and the dilatational part does not play a role in yielding. In other words, yielding is not signified by the hydrostatic pressure which is superimposed on the deviatoric part. Okay. So, he said that that is the by number of experiments empirically, that is how we arrived at. Is that clear? Okay. Now, he looked at this tensor, this is a tensor again, and said that this should have 3 invariants. He called this invariance as J1, J2 and J3. We call this invariance as J1, J2 and J3. What is J1? What is J1? Look at that, 0. Okay. J1, J2, J3 are nothing but obtained from my equation here. This invariance, same thing, because these the 3 invariants are always present. Please note this carefully. These invariants are always present when I look at a second order tensor. So, when I say that tensor, second order tensor, and I want you to write down 3 invariants, okay, these are the invariants. In the same fashion, the deviatoric part also has invariants defined, and these invariants are called as J1, J2 and J3. So, what happens to J1? Trace of sigma here. So, let me call this matrix as S, okay, in order to distinguish this from sigma. Yes, any questions? Any questions? Yeah, so we will call this matrix. Now, what I am saying is this matrix is called S, so that I need not write this down every time. Okay. So, I can say that this matrix is sigma is equal to P plus S, that is all. Sigma is equal to P plus SP. Is that clear? So, the first invariant of my S matrix 0, that is called J. Okay. I do not want, see, I do not want to again write as I, because I already have I defined for sigma, and hence I write this as J. So, J1 is equal to 0. What is my J2? Come back here, come back to this equation here. what happens? What happens to this? That goes off 0. So half, instead of sigma what do I write? Correct. So half Sij Sij. So J2 is equal to half Sij Sij. Is that clear? What is Sij Sij? Just to recapitulate what we did, summation about I and j. Okay, that's the doubt. Clear? Okay. And J3, what is J3? Determinant of S. So J3 is equal to determinant of S. Okay. Now the logic is very simple. If at all there has to be a failure, okay, or yielding in this case, we will not use, sorry, I will not use the term failure. If at all there is going to be yielding, then the yielding should be independent of my coordinate system, obviously. I can't have a coordinate system and say that in this coordinate system there is yielding, another coordinate system it won't yield, and so on. So in other words, my yielding theories logically should be a function of J2 and J3. So my yielding theories should be function of J2 and J3. Just to recapitulate, okay, this whole thing here, what we did was to split this sigma into two parts. By experiments it was shown that dilatational part does not have much effect and deviatoric part has an effect, only has an effect on yielding. So we took this up for further study. Okay. Then we found out that there are three invariants, J1, J2 and J3, three invariants, and out of which J1 goes off by our definition of the deviatoric stress, and hence we have J2 and J3. Okay. So the yielding is a function of J2 and J3. That is what is important. It's a function of J2 and J3. This is where up till this point both Mises and Tresca are on the same line. Okay. Now Mises said that he found rather from experiments that, look, that's not very important. Okay. And for metals, note this carefully, for metals, okay, he found that if I write yielding to be only a function of J2, that is sufficient for me to define yielding. Okay. In other words, what he said is, to put it simply, when J2 reaches a critical value, material starts flowing. Flowing means yielding. Okay. So his whole emphasis was on the fact that J2 reaches a critical value. In fact, he defined the function of J2 to be just J2 and then said that J2 has to reach a critical value. Is that clear? Okay. This theory, ensuing theory from Mises, is also called by the name J2 flow theory. J2 flow theory. Is that clear? So someone says I am following J2. In fact, many manuals say that what we follow is a J2 flow theory. What it really means is that they are following what is called as Mises theory. Is it clear? Okay. Now, what is this critical value? That is our next question. If at all I know, what is that I know from experiments? See, usually there are two sides to the equation. One side, the left hand side, which is J2. We will keep this like that so that if there is a future reference we will look at it. So on one side I have J2. J2 has to reach a critical value, which means that I have two sides of the equation. Right hand side I should have something to do with material. right. J2 depends upon what? J2 depends upon the loading, geometry, boundary conditions and all that, because J2 ultimately depends upon sigma, and sigma depends upon my loading conditions and so on. Is that clear? So, left hand side of this equation depends upon my loading conditions, boundary conditions and what not, geometry and all that. The right hand side should depend upon now the material property. Now, let us look at J2. J2 is square of stress. So, let me call this as say k squared. It reaches a critical value called k squared. What is this critical value? You know, people we talk about all the time critical value. What is this critical value? This can also be looked at some criteria, or people call this also as a criteria function. What is critical value? What is it is in my hands? I can take a specimen and I can load it, okay, look at yielding. That is in my hands. So, in other words, the critical value as far as I am concerned should point out the yielding of the material, or should be related to my sigma y, which I can see, monitor, measure or whatever it is. So, the critical value should depend upon sigma y. So, in other words, what is that I am going to do? I am going to apply whatever theory I have developed so far for yielding for a uniaxial case and see whether I can get the value of k, which should ultimately depend upon sigma y, right. That is what we are going to do now. Any questions so far? Is it clear? The logic is clear? This is a very, very important part, not only in design but also in finite element, because ultimately when you interpret the result, you are going to interpret only in terms of Mises stress. Okay. Usually people interpret finite element results without understanding what is Mises stress. They will just look at the Mises stress and then start interpreting. But actually you should understand that we are applying our well known within quotes failure theories or real theories, and that is how we are doing the whole thing. Okay. Maybe this is not the way you would have studied it in your earlier classes. You would have just got one expression for distortion energy or whatever it is, okay, but this is the logical way in which solid mechanics or continuum mechanics people develop it. It has lot of implications later. Okay. We will stop with just one sentence as to what is a stress tensor for a uniaxial case. So, this is the uniaxial case. What is the stress tensor? Let me have say x1 in this direction, x2 and x3. So, in which case how do I write the uniaxial stress tensor? Let me call this as a sigma 1 or sigma 1 if you want. So, it will just be sigma 1 0 0 0 0 0 0 0 0 period. Okay. So, this will be sigma 1 0 0 0 0 0 0 0 0. Remember that this is only the stress tensor, not the deviatoric stress tensor. What is P in this case? Sigma 1 by 3, and hence I have to subtract that from this in order to get the deviatoric part. We will stop here and proceed to the next part in the next class.